basic agenda today is we'll start out first just trying to characterize when one would use vibration fatigue, looking at loadings. And then we're going to go through and look at key aspects of vibration fatigue, not so much the theory behind it in terms of how we turn PSDs or steady state loads into cycles, but rather how it's implemented inside DesignLife, especially with new features that have come in terms of strain life and composites, seam welds, spot welds. So we're really kind of looking at the implementation of how we're going to use these load providers in other analysis engines. First, just kind of lay the groundwork. When we're doing structural analysis to front-end of fatigue analysis, we actually have a large number of options. We can work basically generating FE results, linear static. We could go in and have either constant amplitude or maybe fluctuating stresses in terms of inputs to a quasi-static. We also can go in and look at the dynamic domain. And the choices there are really us trying to capture the overall physics of the problem. Obviously, we're going to take the simplest approach and take the approach that gives us the most reasonable answer. When we have load frequencies that start to interact with the natural frequencies of our structure, we're forced to take the dynamic route. There's what we're going to need to do is put the loading into our FE analysis and run some sort of dynamic analysis to capture the structural response. In that case, we could take a route where we do the dynamic analysis in the time domain, a transient analysis, and work in the time domain directly, or we can choose to go in and run a dynamic analysis in the frequency domain, either random analysis, steady state. And the choices there, once we have the dynamic analysis in terms of time or frequency, really revolve around the overall loading we're looking at. If we have loads where we can physically predict when things are going to happen, I know on this particular surface of road I have a series of potholes I hit every time, then we want to really go to the time domain. When we have loads that are basically random in nature, steady state dynamic, it makes sense to go in and work in the frequency domain. Just trying to characterize that. Basically, if we take a time history, we can turn that time history by going through basically a fast Fourier transform into a PSD. And the PSD now represents the loading in the frequency domain. What we can do is we can actually go in and take and recompute a time history from that PSD. It will not be the exact same time history that came in because the PSD that we've created basically is missing phase information, but we can recreate a time history that should have all the same statistics. And that's true as long as our input time history was truly random. It was stationary, meaning it's repetitive, and it's kind of got a Gaussian distribution. Now, physically, we can take any time history we have, measure time history, and basically run through that process. But it doesn't necessarily mean that the PSD that I generate out of that time history is representative of my input. And here we have an example where my input history is not stationary. You can go off and see that I have sections that have large amplitude. I have sections that have small amplitude. It's not repetitive, such that PSD that it generates isn't representative of my time history. One of the things we have to kind of step back and think about when we're going to take one route or the other is where are my loads coming from? And again, if I have loads that are coming from things like wind buffeting or wave action or engine vibration, those are very good candidates for going off in the frequency domain and using these approaches. If you have loads where you can go in and know that I have a very predictable load pattern and it changes over time, then the magnitudes change over time, then I probably want to take a time domain approach. Okay, what we're going to do is look at some of the approaches that we have to do the vibration fatigue, working in the frequency domain. And to start off with, if we look at the inputs that we need to run a vibration fatigue analysis, there are really two major inputs. One comes from the final element model, and what this is basically it's called a frequency response spectrum. It's a transfer function. Basically what it's doing is specifying at some load input on my model, these are the outputs that I would see over a frequency range. And so basically it's a frequency response function that allows me to go in now and capture the dynamic aspects of the model. This frequency response function is basically calculated inside of your final analysis as basically either a steady state dynamics or harmonic or solution 111. And what it is, it's a unit excitation, be it acceleration, displacement, force, across a frequency range. And then the output is basically a complex set of stresses or displacements or forces that describe the output at each node on my model. The other input is then brought into DesignLife is basically the actual loading that we're going to apply to the structure at those excitation locations. And these could be PSDs or swept signs or signed welds. With this information, DesignLife can go in at every location and generate a PSD of stress that we're going to go in and calculate the fatigue on. Now this FRF actually can be calculated in a couple different ways inside the final element program. One, I could go in and run my steady state dynamics and basically directly out of that analysis capture the stress at every frequency step that I want. And so these stresses would be across the entire model. They'd be real and imaginary components. And so I would have a direct FRF coming out of my final element program. Most times when we're doing these calculations, we're doing the frequency response function in the modal domain to begin with, because it's far more efficient than going off and actually using the nodal degrees of freedom as my inputs. And so we're already doing a modal-based calculation. In that case, we're able to go in and basically split apart the frequency response function into two pieces. So I'm going to go in and run a steady state dynamics or a harmonic analysis of solution 111, but the first step is I actually run a modal analysis. The modal analysis looks at the structure in terms of stiffness and mass and gives me the natural frequencies and the mode shapes. And from that analysis, I capture the stresses that would be occurring on my model if I were to go off and enforce those mode shapes onto my model. So these are modal stresses. This modal information is then also used as basically as an input to the harmonic analysis. And that information is used to go off and create basically the, the frequency response function. But in this case, all we're really capturing are going to be the real and imaginary scale factors versus frequency that we'd apply to each mode. So this would be a table of information, frequency versus real and imaginary scale factors I'm going to apply to basically capture each mode in my structure. Now what I can do is I can bring in these modal stresses, I can bring in these tables of complex scale factors versus frequency, and I can put them together inside of DesignLife and create the FRF directly. The reason we look at this, even though it seems very complex in terms of what things I have to do, is it has the ability to create far smaller files, because I'm looking at here at kind of a fictitious analysis I want to run where I was going to run through a frequency range with a frequency increment such that I have 200 steps. Basically, I'm going to have 200 frequencies I'm saving results at. If I were to take the director route, at every one of those 200 steps, I would have saved a complete set of stresses for my model, both real and imaginary. If I take the modal superposition route, I'm looking at here where I actually have 10 modes in my structure. And all I have to do is capture the real stresses, the modal stresses for those 10 modes. And then the harmonic information is going to be saved as tables, but just very short tables that basically are going to be, for every mode, just the real and imaginary multipliers at the frequency steps. And especially when I want to have a high resolution in terms of frequency and maybe a large frequency range I want to capture, this modal approach is far more efficient in terms of model size. It becomes even more powerful when I'm going to go in and have multiple FRFs calculated in different directions, because now I can use the same modal shapes for all my inputs. So when possible, this actually has significant benefits in terms of dramatically reducing the file size. And once we have the file sizes down, actually the overall analysis speeds up. So we have that as a technique we can go off and use for our dynamic, for basically our vibration fatigue analyses. What we're going to do is look at a case where I have multiple inputs going into vibration fatigue. And again, we can look at this in a couple different ways. One, many times when we're doing physical tests, we're running an equipment that basically is forced to run in a single axis. I may want to qualify my component in multiple axes, but I'm required to run them one at a time. And we can do that in DesignLife. So what we'd end up doing is taking our component, running an excitation in the X direction, stopping, running excitation in the Y direction, stopping, run it in the Z direction, and then physically sum up the damages from each of those different excitations. And that would be basically modeling a virtual shaker table. That's many times how the shaker table test is run. However, in real life, we know that our component doesn't see these individual directions one after the other. They're combined together and run simultaneously. And so we have the ability inside DesignLife to run basically a virtual shaker table, which is running individual single-axis tests one after the other and using a duty cycle to basically combine together the damage to simulate the shaker. Or we can go in and we can actually apply individual PSDs simultaneously and look at the overall excitation as we see it in the real world, or actually see it in a multi-axis shaker table. If we're going to go in and take the approach where we have multiple simultaneous PSDs, we need to have a PSD for each direction and load point in our structure. So we'll have multiple PSDs coming in. However, when we have more than one loading going into a structure, we have to capture the phasing between the loading. And remember, the PSDs do not have any phase information. So what we need to bring in is for every pair of PSDs coming in, we need to bring in what we call a cross-correlation matrix. So this cross-correlation matrix is basically cross-spectra and phasing between the two sets of loads going in. So those would be my inputs coming in. If I have 3 loads coming in, I end up with basically 3 PSDs and then 6 cross-spectra coming in. If I had 10 inputs coming in, I'd have 10 PSDs and basically 90 cross-spectra coming in. So the cross-correlation information starts to become very large very quickly. But they come in as our loading, And again, the frequency response function could be a direct response function, or it can be modal. And again, here modal actually has a tremendous advantage because it's one set of mode shapes, and then all the different inputs coming in terms of frequency response are calculated, are just basically the modal coordinates. So we take the FRFs, we apply our PSDs and cross-correlation matrix, and we can go off and calculate the overall combined fatigue damage. And again, when I do a simultaneous PSDs, we're actually applying all these things simultaneously. We're basically summing up the stresses prior to damage calculation. When we look at the virtual shaker table, we're going off and running individual sets of stresses, calculating damages, and superimposing the damages. Now, I'd already mentioned that as we look at this multiple PSDs, things start to become fairly complex in terms of managing data. If we bring in the modal approach, it becomes even more so. And so inside the load provider for vibration fatigue, you'll see that there actually is multiple tabs coming in. And the first tab is to manage this modal superposition. What it does, it brings in and pairs up basically the modal stresses from a finite element analysis with a set of multi-column modal coordinates. You'll have one of these sets of modal coordinates for each mode shape in your model. This would allow me to go in and generate individual FRFs that could be applications of excitation at different locations or different directions. In this example here, we basically have one set of modal stresses, and then we had basically the modal coordinates for going in and exciting it in 3 different directions, X, Y, and Z, and it generates 3 FRFs that I'm bringing into the next step of the analysis. The next step of the analysis, I take those 3 FRFs and I pair them up with a series of modal coordinates, PSDs, and cross-correlation. Again, if I have 3 FRFs coming in, I'm going to have 3 applied PSDs and 6 sets of cross-correlation matrices, and things start to be, again, fairly difficult in terms of keeping and managing the data. What we have coming along with vibration fatigue is a process, we call it the cross-PSD process, and its purpose is twofold. First, it generates the input PSDs and cross-correlations for me. Again, what I need to do to actually capture the cross-correlation information, this is basically how one load input interacts with another. I actually have to start with a time series because it's the time series data that actually had this phasing information. So it brings in the time series information, and then it'll generate for each time series a PSD. It'll generate for each pair of inputs cross-correlation matrices. And then, more importantly, it generates a loading file that will go in and can be imported into vibration fatigue to automatically assign all these inputs inside of vibration fatigue. So I can automatically just go in, pick that file, and have it populate my inputs for the multi-PSD. As I had said, one of the things that we've been working on in the last couple of releases is taking the vibration load provider, again using frequency domain dynamic analysis, and applying it to other engines. Historically, it's been stress life only, parent metal. And so we've actually gone in and enhanced the other engines by bringing in the vibration load provider. One of the ones we've done it for is strain life. If you were to look at what the vibration load provider does, it goes in, brings in the frequency response function, brings in an input PSD or swept sign, and it generates a PSD of stress. And then we have ways inside DesignLife to take that PSD of stress and cycle count it. These cycle counters, the narrowband approach, Steinberg, Derlick, Lalande, look at the PSD of stress and generate a histogram of cycles. So it's creating a histogram of cycles. And in StressLife, that's perfectly fine because I can take each one of those bins in the histogram, take its magnitude, mean stress, and calculate fatigue damage and sum up the damages. In StrainLife becomes far more complex because we're going to take the information, the stress, linear elastic stresses or strains, and we're going to do plasticity on them. We're going to basically do a plastic correction using Neuber, Hoffman, Seeger. And one of the things with plasticity is it's path dependent. The elastoplastic corrections basically are dependent in the order I see the cycles. Once I have it in a histogram, I've lost that order. And so what we need to do the StrainLife calculations is we're going to work on a histogram of stress cycles, and we have rules built in, basically how to count, how to do the plasticity. What we're doing here is we'll go through the stress cycles and we'll identify the cycle that basically is the largest load, and that generates an outer loop. Again, once I do plasticity, I'm going to see hysteresis loops, stress-strain behavior come out of just the elastic results. Once I have the outer loop, we have rules-based built in then that go in and look at each other cycle. And each cycle now we know has to be in that loop, but we're not quite sure where. So what we'll do is calculate two sets of damages for each cycle. One will be a best case scenario, the other will be a worst case scenario in terms of damage. And so we're basically choosing the mean stress and the stress levels from the histogram to give us a worst case scenario. We're also calculating the mean stress position in the histogram to give us a best case scenario. And we go in then and average the lives. So we're going in and basically doing the plasticity on the histogram, and we're taking basically the two extremes and giving you basically an average life from that. So that's the implementation inside of StrainLife. And from a process point of view, the only difference between running StrainLife in the time domain and running it in the frequency domain is the load provider. So now, basically what I have is I have an input PSD. What I'm going to do here is I'm going to jump to another application. And bring up DesignLife. So what I have here is a DesignLife process. What we're looking at is a simple exhaust system, and actually we'll see this exhaust system several times today. What we have are constraints at the exhaust manifold, and we have excitation at the hanger at the other end of the exhaust. And the excitation is going to be a acceleration PSD. In this case here, we're looking at strained life. And so what I have is an input PSD that I'm applying. So this is a PSD that I have specified I'm going to apply to the hanger. I have a load provider, vibration load provider. And here I've actually driven this from a modal analysis. So what I have here is I actually have a load case 1 that was the modal stresses coming out of my final analysis that were used as the input for my steady state dynamics. And then I have a multi-column file that is the modal coordinates. that multi-column file actually came in the Moodle coordinate input. So I have basically Moodle coordinates coming out of my fund element. I have a solution that has modal stresses, and the first tab is going in and basically putting the two together to create a frequency response function. The second input inherits that frequency response function, and you'll see it says for modal, and then I apply to that my PSD. And so basically that is my input FRF, and I'm basically applying a PSD that came out of the vibration generator that I showed you the profile. So that's basically the load provider. Actually, while I'm here, you could also bring in static load cases to make basically mean stress shifts on the model. You could also bring in temperatures, and I'll show you, I won't run the analysis, but I'll show you a PowerPoint right after this, where I've actually done a thermal analysis. And so I have an isothermal strain life with the fatigue solver in it. The other aspect of this is the fact that I am running strain life, and so I have now a material model have to find it. Oh, okay. Try this again. I have basically strain life material model here. If I go in and jump to I can go in and basically look at my material in terms of strain life. Cyclic stress strain curve, strain life curve for the fatigue analysis. So we're actually going off here and doing strain life, low cycle fatigue on this analysis. Let me go back to my PowerPoint. So that was strain life analysis. As I mentioned, I also ran an analysis with a temperature input. So along with the modal stresses, I brought in a separate model that had temperatures at every one of the nodes, and up at the top right-hand corner, you can see the temperature map. And we've brought in and applied as a third part of my vibration input that temperature profile. And in terms of material properties, we've actually gone in and brought in not a strain life curve, we brought in a whole family of strain life curves at different temperatures. So I can go in and actually do isothermal fatigue analysis in the frequency domain with this. So that's strain life. And again, this gives me the ability to go in, use my frequency-based loading and apply more low cycle fatigue behavior. In addition to strain life, we've actually applied vibration fatigue to our short fiber composites. And so a short fiber composite analysis, what I'm looking at is a material many times just injection molded, where I have two components to the material. I'll have a plastic matrix and I'll have a reinforcement fiber, glass, carbon fiber. Because of the injection molding, the material becomes directional. The fibers start to align, not only across the part, but through the thickness of the part. And so now I do not have an isotropic material any longer. I have an anisotropic material behavior, and I have to basically deal with the differences in strengths, both in my final analysis, excuse me, but I also see it in my fatigue analysis. So this becomes an analysis where all of a sudden I need to go in and look at the manufacturing solution in order to start to do my structural analysis, hence my fatigue analysis. I don't want to spend a great deal of time here, but if one looks at a process flow, the starting point is basically the simulation of the injection molding. And coming out of that, I get information on fiber orientation, fiber density, basically some aspects in terms of fiber sizes. And it's possible to take that information and compute basically structural properties to go into the final analysis. So we can go in and basically generate for each location, each layer in the part, a anisotropic definition for elasticity, or it could even be more complex, elasto-viscoplastic. Once I have that, we can go off or do our solution and get stresses. Again, now these stresses came out of a directional structural model. So I have now stresses basically I'm going to have to look at in multiple directions. We need exactly the same manufacturing information, the fiber orientation information, to do our fatigue analysis. We actually have 3 different fatigue damage models available for this. We're going to look at just a simple one today, which is basically just a stress life approach. But here, each of the curves in stress life are looking at a different direction in the composite. So I have curves looking along the major direction where the fibers would be going. I have curves that also look perpendicular to that and curves in between. With this model, I can then go in and run a fatigue analysis. So I'm bringing in basically orthotropic or anisotropic stresses, and then I have a fatigue model that's going off and looking at a critical plane analysis, either in plane or full 3D, looking at different directions. And then with the fiber orientation information, I can go in and choose the appropriate stress life curve to go off and do the fatigue calculation. So this is basically a process where we've brought in a model out of finite elements that basically the input information in terms of material properties and orientation actually came from Moodle 3D in this case. We use that exactly that same information in terms of fiber orientations in the fatigue analysis and applied to that a material that was a nylon glass-filled polymer. Are able to go in and apply the PSD loading to the dashboard here. In this case, the PSD was an excitation in terms of gravity loading on the dashboard. So we had mount points on the dashboard where the polymer dashboard where it was matched to the car body, and we have basically gravity oscillating based on the PSD. And coming out of this, what we have is maps, life, damage. We also can go off and extract out of critical locations things such as the PSD of stress, the distribution of cycles, and we'll see these as we go on later on as well. How are we doing here? In addition to strain life, short fiber composites, we've actually gone in and implemented part of the seam weld capability with vibration fatigue. And again, I'm assuming you kind of are somewhat familiar with vibration fatigue, but some of the new engines were new to you. So I was going to walk through some of the capabilities that, or some of the challenges that we have with seam welds. Welds in general are very difficult to analyze. We can't use the standard approaches that we use for parent metal because we basically do not have detailed geometric models of the weld itself. We also don't have detailed property distributions. If I look at a weld has basically many times added material to the model, the weld metal. It's transformed some of the other metal, heat-affected zone. It also has generated very difficult geometries in terms of weld toe and weld root to actually calculate. So we use other approaches for dealing with this. One way we have is what we call a Volvo approach that is basically shell-based, and that's what we'll focus in on today, where I model the weld as an extremely simple shell model. One or two basically weld elements representing the connection between the parts. But this allows me to go in and model a structure that may have tens of meters of weld in it and allow me to model the welds using this simple coarse approach. We use structural stresses. Because we're using such a coarse model, we can't trust the stresses at the locations of the welds. So what we do is we basically back calculate what we call a structural stress, and these stresses are not the actual stress at the weld toe or the weld root, but they're a stress quantity that kind of represents the load going through the weld, and we use those structural stresses as our damage parameter. The implementation we have today is actually stress-based. We also have, for the seam weld, a grid point for it, a node point force and moment calculation. That has not been, we have not applied the vibration fatigue to that in the current release. So it's basically using stresses only. In order to get the structural stresses to actually converge for us into, against test data, we actually have to account for where the stresses came from. Basically, we're using a relatively low value of stress to measure the load going through the model, but the actual critical location in the weld has a much higher value of stress. There's a stress concentration factor built into our SN curves. And in order to make this basically work, we actually have to account for the fact what caused the stress. So we're automatically going in and calculating how much of the stresses came from bending versus how much of the stresses came from tension. And we make those bending corrections automatically. It's internal to the software, but though this is the challenge with vibration fatigue, because one of the things we actually have to do is be able to go in and look at the top and bottom of the shell and make these bending corrections. There's thickness corrections going on, that's pretty standard for fatigue. And then what we have, one of the hallmarks of welding is that when you look at the weld behavior, it usually doesn't reflect the strength of the parent metal. And so we're able to actually go in and use generic curves for steel, generic curves for aluminum when we're looking at welds. So that's kind of the basic weld approach that we've had for years in the time domain. What we've done is we've implemented this in the frequency domain. So we've taken the vibration load provider and basically tied that to our model. So we're back looking at our exhaust system, and if you looked at our exhaust system, I have two areas where I've welded. I have a bracket welded to the exhaust tube, and these welds here are what we call fillet welds. They're welding plates that are basically perpendicular to one another. I also have a second weld farther up on the exhaust system where the exhaust tube goes into the muffler. You can see basically like blow up here, where basically the purple elements represent my weld elements, and they're basically welding the outlet tube of the muffler to the exhaust tube. So I have two different configurations of welds. These welds we call overlap. These welds here we call fillet welds. And what we're getting out of these welds are stresses, in this case on an Astran, that are structural stresses. So we're actually looking at the stresses along the toe and the roots of the welds to do the calculation. So in here, I've pointed to the two sets of welds, the fillet welds that were at the bracket, the overlap welds that are at the tube muffler connection, and have applied, again, a TSD input at the bracket and calculating the weld fatigue. using, again, a spectral approach. Again, you can come down and see my input PSD at my critical weld, the PSD of stress that was calculated, as well as the histogram at that location that was the counted cycles, and there's a second histogram here that's actually the damage for this. So same model, now I'm focusing on welds versus strain life for the exhaust. And then finally, just look at spot welds. Again, we've brought in the vibration load provider to spot weld as well. And for those who aren't familiar with spot weld is looking at a structure where the welds are represented. A spot weld is nothing more than basically a weld where I have fused a small diameter together. And the way that we model this in finite element is we go in and just connect to two flanges that have been welded together with a simple beam element. Now, there's other modeling techniques you can use here. We have an area contact method that uses multi-point constraints and solid elements. There is some specialized fasteners, things such as C-weld. There's also a method that uses pentas rather than hexas as an area contact as well. We'll just focus in on the beam model. They're all these are actually supported though. So from the beam element, what we get out of our final solution is forces and moments. The assumption here is that my shell mesh isn't fine enough to give me stresses, so we're going to go in and take forces and moments out of the beams and use those in a empirical shell model to calculate stresses. Now, historically, this was in the time domain, so the forces and moments were basically functions of time. What we're bringing in now are the frequency response functions of force and moment that were calculated in the finite element, and we're using those to calculate the stresses around the perimeter of the weld. So what we have here are stresses calculated around using a theoretical shell model around the perimeter of the weld, and again, it's just basically looking at the individual stress components created by each of the different forces and moment components. And I now have a whole series of stress histories around the perimeter that we go in and do the calculation on. However, now they're no longer histories, they are PSDs. Again, we're bringing in inputs that would be a PSD input to my structure. I get forces and moments out that are now frequency response functions. From there, I can calculate a PSD of stress at every point around the perimeter of the weld nugget and use that to do the weld fatigue. And again, going back to my exhaust model, the back of my exhaust model, we put a heat shield around the catalytic converter, and a heat shield is actually assembled with a series of spot welds. So I have here a series of spot welds on both the front and back side that hold it together. So it's these spot welds we're doing the calculation on. Now, in spot welds, we actually account for looking at both sheets that are being welded together. We also look at the failure in the nugget. And so in this case, we're looking at 36 locations around the perimeter of the nugget on the top sheet, 36 locations on the bottom sheet, and 36 locations around the nugget. So it's 108 locations we do the calculation at. What you see coming back is the worst case. So out of those 108 locations, this was the location that gave me the lowest life, longest, most damage. And again, same basic input in terms of the PSD. Here the dynamic response is very, very different because we're looking at this aluminum heat shield that we're exciting versus the exhaust system. And again, using the PSD of stress to count cycles and calculate the fatigue damage. So what we're looking at here is the fact that we have at times the need to do dynamic analysis, and the vibration fatigue load provider is an excellent choice for doing that especially when our inputs are random or harmonic. We also see that we can go in and utilize, when we're doing a modal harmonic analysis, actually leverage mode superposition, save only the stresses from the mode shapes and then the modal coordinates from the harmonic analysis, and with that we can significantly reduce the file sizes and hence speed up the analysis. We can go in and using vibration fatigue, we can simulate what we do on a shaker table with basically a sequential set of PSDs where we sum up the damages. We can also go in and apply PSDs simultaneously, and we have built in to the software flows that allow us to go off and generate all the inputs necessary to support that multi-PSD analysis. And then finally, at 12.1 and 13, we are introducing the vibration load provider into whole new engines. And we talked about the fact that we have strain life, we have the short fiber composite, seam weld, and spot weld.